Welcome to the deep dive. Today we're digging into something called PeerDAS, which is pretty central to Ethereum's plans for scaling up.
Yeah, it's a really interesting piece of the puzzle.
So imagine Ethereum, the blockchain, is like this enormous library. Right now, every visitor that's like a node basically has to, well, at least flip through every single page of every book to check that all the data's there. Nothing's been messed with.
Which, as you can imagine, is a huge amount of work, especially as that library just keeps getting bigger and bigger.
Exactly. It doesn't scale well. So PeerDAS comes in with a different idea. Think of having specialist librarians. These are our light clients. Instead of everyone scanning everything, these librarians just pick, say, a random word on a random page here and there. And if enough of them report back that the words they checked are correct and present, then everyone can be, well, pretty confident that all the books are actually complete and untampered with.
Right. It's probabilistic. You're not checking everything, but you're checking enough random spots that the odds of missing a large chunk of missing data become incredibly small. That random checking, that's data availability sampling.
DAS, yeah. So for this deep dive, we're looking at PeerDAS based on, the latest research, community discussions. It's positioned as this intermediate step towards the full DAS vision, especially important for making layer 2 rollups work better.
Which is crucial for scaling.
Absolutely. So our mission today, especially for you listening, if you've got a good handle on blockchain basics, maybe you're a developer in the Ethereum space, is to really unpack PeerDAS, understand the tech behind it, how it works, and crucially, where it fits in the bigger picture of Ethereum scaling. Ready to jump in?
Let's do it. Maybe start with a high-level picture, a mental model.
Good idea. Okay, so think about those layer 2 rollups. They bundle up a whole load of transactions off-chain. Instead of putting one massive data dump onto Ethereum layer 1, they break it down into smaller pieces. We call these blobs.
Right, like packets of data almost, smaller, manageable chunks.
Exactly. Now, what happens to these blobs?
Okay, so each blob goes through something called Reed-Solomon encoding. It's a type of erasure coding. Think of it like this. You take your row of data, the blob, and you add extra mathematically related data onto the end of it. It makes the row longer, but it adds redundancy.
Redundancy, meaning if you lose some parts, you can still figure out what the original was.
Precisely. It's like adding parity bits in computing, but, way more advanced. This redundancy is key because it means even if some nodes on the network don't have certain pieces of this extended data, you can still reconstruct the original blob if you have enough other pieces.
Gotcha. So that protects the data within each blob.
Exactly. So step 1. Split into blobs. Step 2, add redundancy to each blob using Reed-Solomon, making them extended blobs. Now, imagine you take all these extended blobs, these longer rows, and you stack them up one below the other. You form a big grid, a matrix.
Okay, rows are extended blobs.
Right. And what PeerDAS actually samples, what the light clients check, are the columns of this matrix, these vertical slices, through all the different extended blobs.
Okay, so the protection runs horizontally within a blob, but the sampling runs vertically across blobs.
You got it. It's a clever structure. Now, to make this efficient for those light clients, remember, there's supposed to be lightweight PeerDAS generate something called a commitment for this whole matrix of data.
A commitment, like a summary.
Yeah, think of it like a very small, unique fingerprint, like a hash, but with special cryptographic properties. It represents the entire data matrix. Light clients download just this tiny commitment first.
Which is obviously much, much smaller than downloading all the blob data.
Orders of magnitude smaller.
Yeah.
So when a light client wants to check if the data is actually available on the network, it uses this commitment. It sends out requests to various nodes asking for specific pieces, random samples from those columns of the encoded data matrix.
And because of the Reed-Solomon redundancy?
Exactly. Because of that redundancy, even if it only gets back, say, 70% of the samples it asked for, if those samples match the commitment, the math ensures it can be highly confident that all the original data was available somewhere on the network when the commitment was made.
So the redundancy makes the sampling meaningful. It's not just for reconstructing lost data later. It's fundamental to how the sampling proves availability.
That's the core insight. The whole system, blobs, erasure coding, commitments, sampling it, lets these light clients verify gigabytes of data availability by only downloading kilobytes.
Okay, that mental model helps a lot. Let's maybe layer in some more technical specifics now. We mentioned data availability sampling, DAS. Can we define that a bit more formally?
Sure. So DAS formally is a technique allowing clients on a P2P network to check that some piece of data is fully available within the network without downloading the whole thing. They do this by requesting random samples of an encoded version of the data and verifying these samples against a succinct commitment.
Succinct meaning small, fixed size.
Right. And the whole thing relies on that underlying assumption that the data has been redundantly encoded like with Reed-Solomon and is distributed across the network nodes.
And PeerDAS is Ethereum's sort of first big implementation step towards this.
Exactly. It's not the final full DAS vision yet, but it implements the core sampling logic and introduces the essential cryptographic components needed for it. It's like building the engine before you finish the whole car.
Right. And this is all driven by the need to support rollups better. Remind us why data availability is so critical for them.
Okay, so Ethereum mainnet has limits on how much computation can happen per block the gas limit. Rollups get around this by doing the computation off-chain on layer 2. But crucially, they still need to post the transaction data back to layer 1
Why? For security.
for security and liveness. Anyone needs to be able to look at the data posted on layer 1 to verify the rollup state transitions, or in a worst-case scenario, to force withdrawals if the rollup operator misbehaves or goes offline. If that data isn't available on L1, the whole rollup system can grind to a halt. You can't prove the state, you can't exit. It's a major problem.
So layer one's role becomes guaranteeing that data availability for all these layer twos relying on it.
Precisely. Which brings us to EIP 4844. That was a precursor, right? How did blobs come about?
Yeah, EIP 4844, sometimes called proto-danksharding, was huge. It introduced a new transaction type that could carry these blobs of data.
Huh.
Blobs are separate from the usual transaction call data and, importantly, priced differently, much cheaper for storing large amounts of data. They also have a shorter lifespan on layer 1 nodes. They don't need to be stored forever like state data. This
Yeah.
made it economically viable for rollups to post their transaction batches. PeerDAS basically builds directly on this blob infrastructure.
Right. So the blobs provide the dedicated space. And now PeerDAS adds the sampling mechanism on top. You mentioned Reed-Solomon codes for redundancy. How exactly does PeerDAS use them?
Okay, so it takes a data blob. Mathematically, it treats the data in that blob as coefficients of a polynomial. Let's say the blob has k pieces of data. It then evaluates this polynomial at, say, 2k points, twice as many points as original data pieces. This longer sequence of evaluated points is the Reed-Solomon code word, the extended blob. The magic is, even if you lose up to half of these evaluated points, you can still uniquely reconstruct the original polynomial and thus the original k data pieces.
So it effectively doubles the size but makes it resilient to 50% data loss.
Exactly. And this extension happens individually for each blob before they're arranged in that matrix we talked about.
Okay, and for each extended blob, each row in our matrix, PeerDAS uses KZG commitments. What are those about?
KZG commitments are pretty neat. They're a type of polynomial commitment scheme. Basically, you can commit to a polynomial like the one representing our extended blob with a very small constant size commitment value.
Right.
And the cool part is you can then create very small proofs to show the value of the polynomial at specific points. Even better, you can create a single small proof called a multi-proof that simultaneously proves the polynomial's value at multiple points. PeerDAS uses a specific kind of multi-proof called multi-proofs over cosets, which is efficient for the way it structures the sampling points.
So these KCG multiproofs let a node prove to a light client, yes, the data points you requested are consistent with the commitment for this extended blob. And it can do that very efficiently for many points at once.
Precisely. It avoids having to send large amounts of data or generate huge proofs.
This ties into the idea of an erasure code commitment. What extra guarantee does that provide?
Right, so a regular commitment just binds you to some data. An erasure code commitment, specifically in this context, adds another layer. It ensures that any valid proofs or openings you provide for different points within an extended blob are not just consistent with the commitment, but are also consistent with some valid Reed-Solomon code word.
Meaning you can't just make up data points that match the commitment individually, but don't fit the overall error correction structure.
Exactly. It enforces the integrity of the encoding itself. We talk about properties like code binding, ensuring it's a valid code word, and position binding, ensuring you can't claim different values for the same position later.
Got it. Okay, so let's trace the encoding path for one blob again. You take the blob data,
Treat it as polynomial coefficients.
evaluate that polynomial at a larger set of points, often related to roots of unity and finite fields, to get the Reed-Solomon extended blob.
Group contiguous evaluation points into chunks called cells. These cells become the basic symbols or units within the extended blob row.
And then you generate a KZG commitment to this entire extended blob row. And when you have multiple blobs, you stack these extended, committed rows into the matrix.
And the columns of that matrix become the symbols that PeerDAS actually samples across the network. Light clients request random column data.
Okay, that clarifies the structure. What about the security underpinnings? Things like the DBSDH assumption or the algebraic group model. What's the gist there?
Right, so the security of the KZG scheme, and thus PeerDAS, doesn't come out of thin air. It relies on the assumed difficulty of certain mathematical problems in elliptic curve cryptography. The D-bilinear strong Diffie-Hellman, or DBSDH assumption, is one such standard, widely studied hard problem. Breaking KZG is believed to be as hard as solving DBSDH.
So it's tied to established cryptographic hardness assumptions.
Exactly. The algebraic group model, or AGM, is a theoretical model sometimes used in security proofs. It basically restricts the kinds of operations an attacker can perform on cryptographic elements. It simplifies proofs, but ideally you want proofs that hold even outside the AGM against potentially more clever adversaries. It's an area of ongoing research to strengthen these proofs.
Understood. Standard practice in crypto proofs. Now, the sampling itself, you mentioned a number, like 75 samples, was discussed somewhere. How is that number determined?
That number, roughly 75, comes from probability. The goal is to ensure that if, say, a quarter or more of the data is actually unavailable, the chance of a light client picking 75 random samples and all of them just happening to land in the available portion is extremely tiny, like less than 1 in a billion tiny.
So it's about confidence. With 75 samples, if they all check out, you're incredibly confident that at least, say, 75% or maybe even more of the data must be available.
Exactly. Each sample is an independent check, and the probability of repeatedly missing a large unavailable chunk drops exponentially with the number of samples. 75 is roughly where you hit that cryptographically secure level of confidence against a significant fraction of missing data.
And verifying these 75 samples individually would be slow. That's where batched verification comes in.
Yes. Instead of running the KZG verification logic 75 times, there's a mathematical technique using random linear combinations. You combine all 75 sample checks into a single, slightly more complex check involving pairings on the elliptic curve. It's much faster overall.
It usually involves a random challenge, generated perhaps via a hash function modeled as a random oracle, to prevent certain attacks on the batching process itself.
That's right. It ensures the batch verification is sound.
Okay, and if the sampling succeeds, we're confident the data is available. But if we do need to reconstruct a blob because parts were missing, how efficient is that?
Thanks to the Reed-Solomon properties, if you have at least half of the cells, those groups of evaluations, for an extended blob, you can recover the original polynomial using interpolation. There are efficient algorithms for this, often leveraging fast Fourier transforms, FFTs, and related techniques like using vanishing polynomials to do this reconstruction much faster than naive interpolation.
So both verification and potential reconstruction are designed to be efficient.
Definitely. Let's put some concrete numbers on this, what parameters are actually used.
Okay, so PeerDAS typically uses the BLS 12381 curve, which is common in Ethereum now. Field elements are 32 bytes. A cell, that basic sampling unit within a row, is often defined as 64 field elements.
So about 2 kilobytes per cell.
Roughly, yeah. An original data blob is specified as 4096 field elements. That translates to 64 cells, or 128 kilobytes, 217 bytes.
Okay.
The Reed-Solomon encoding extends this 2x, so an extended blob becomes 8,192 field elements, which is 128 cells, or 256 kilobytes, 218 bytes. The number of blobs stacked together in the matrix, often denoted RU, is still something being finalized and might be dynamic.
Right, depends on network needs. Okay, so zooming out again, how does all this fit into the big picture for Ethereum? Where does PeerDAS land?
PeerDAS is slated to be a major component of the next big Ethereum upgrade, currently codenamed Pectra.
Pectra, what's the focus there?
Pectra's got several goals, making staking easier, improving account abstraction, but a huge theme is scalability and network stability, building on previous upgrades. PeerDAS is arguably the core piece delivering on the scalability front within Pectra.
So it's pretty high priority.
Seems likely, yes. Its success is really foundational for Ethereum's roll-up-centric roadmap. It directly enables Layer 2s to become cheaper and handle more data securely. For developers building on L2s, this is a massive unlock. Better data availability means potentially higher throughput, lower fees, and maybe even new types of applications that weren't feasible before because of data constraints.
And we should stress again, PeerDAS is a step. The long-term goal is full ding sharding, full DAS, which would scale this even further.
Absolutely. PeerDAS gets the sampling mechanism working in production, proves out the crypto components like KZG, but full DAS aims to integrate this even more deeply and potentially increase the data capacity significantly more.
Are there trade-offs? What's the cost of implementing something like PeerDAS?
Well, the main trade-off is complexity. The cryptography involved erasure codes, KZG commitments, batch verification is significantly more complex than just storing data directly as call data was. It requires more sophisticated client software and careful implementation. But the benefit, that huge boost in scalable data availability for rollups, is seen as well worth the added complexity.
Makes sense. Okay, so let's try to wrap this up. If someone, maybe a developer, takes away just a couple of key points about PeerDAS from our chat, what should they be?
I'd say, 1, PeerDAS is Ethereum's practical step towards data availability sampling coming in the Pectra upgrade. 2, its main goal is boosting scalability by making it cheap and secure for Layer 2 rollups to post their data to Layer 1.
And 3, it achieves this using a combination of Reed-Solomon codes for data redundancy and KZG commitments for efficient verification, allowing light clients to confirm data availability by sampling just small, random pieces.
Exactly. It lets light clients do their job without being overwhelmed by data, which is crucial as Ethereum continues to grow.
All right, so here's a final thought to leave you with. PeerDAS promises this much stronger, more efficient guarantee of data availability. How might that fundamentally change what's possible on Layer 2? What new kinds of decentralized applications could developers build, knowing that this foundation is there? What doors does this open?
That's the really exciting part looking forward. The possibilities could be quite broad.
Definitely something to think about. We highly recommend diving into the source materials if you want to get even deeper into the technicals. Thanks for joining us for this deep dive.